Hi, so today I'm going to look at the kinematics topic, which would be the last lesson, if you like, of this week. And this is something that came from an earlier chapter that we skipped at the time, but now we've kind of done a lot of differentiating in calculus, it makes sense to revisit it. So if you haven't heard the word kinematics before, all it essentially means is motion. So things like velocity, position, acceleration. So it describes how things move. And really it's a bit of maths that kind of belongs in mechanics. And it's the only real bit of mechanics that in the IB is in the maths course. The rest of it would all be in physics. So I'm going to start by just considering some of the things that you might have seen in physics or in science when you're younger. So that's this red box over here. So these two equations, you probably have seen before. So velocity, and you might have seen it described as speed, being distance over time, and an acceleration being change in velocity over time. So you will probably have seen those equations in your science lessons when you were a bit younger. And if we bring that onto a graph, so I've drawn the graph in advance here, and this is a position graph, although I've written VT, I should have written ST. This is a position time graph or a distance time graph. And the scenario here is, suppose this is you cycling to your friend's house. So you start off at your home here, and you take half an hour to cycle to your friend's house, and your friend's house is 8 kilometres away. So you cycle fairly slowly because it's uphill. Then you stay at your friend's house for an hour, so 0.5 to 1.5 on my time axes, and then you cycle back home. And because it was uphill on the way there, it's downhill on the way home, so it takes you less time to cycle home. So this tells us the position. So initially we're at position 0, then our position increases linearly until we reach 8 kilometres, then we stay at that position for an hour, and then we come back towards our origin, or in this case, your home. And if we were to take our velocity equation and compare it to this graph, that would come from the gradient of the graph. So distance, so if we're looking at the velocity of the first little section, the distance is 8 kilometres, and the time, and I'm going to do it in hours, so half an hour. So if we wanted velocity, we do distance over time. So we do velocity is 8 over 0.5, and we'd get 16 kilometres per hour. And because we're doing distance over time, on the distance time graph, that's just the gradient. We could do the same thing on the way home. And the only difference on the way home, so we'd still have a distance of 8, and we'd have a time, this time it's quarter of an hour. But the difference on the way home, and this time we're going really quickly, the difference on the way home though is that our velocity would be negative. If we think about gradients, that makes sense, the gradient's negative, but it's because if you haven't come across this yet, velocity has to include direction. So it has to include, are you going away from the origin or towards it? Are you going in the positive x direction or in the negative x direction? If it was just speed, I wouldn't need the plus or the minus. So on these graphs, we can say that the gradient of a position time graph or a distance time graph is velocity. And if I do a velocity time graph, its gradient would be acceleration. But the problem with these kind of scenarios is that they're not that realistic to what really happens. If you think about this example of cycling to your friend's house, you don't start at your home and then immediately go at 16 kilometres an hour, right? You have to start pedalling slowly and then you gradually speed up. So a more realistic graph like this might look a little bit more like this green line. So you start off really slowly, your distance only increased a little bit at a time, but then as you kind of gain momentum, you start to go a bit faster. And again, when you come to a stop, you don't just stop immediately. You don't go from 16 kilometres an hour to 0 in like instantaneously, unless you hit a brick wall. But, you know, what we really do is use your brakes, right? So you would slow down gradually until you reach the stop. And if we think of that in terms of gradients, it means that initially my gradient's quite shallow. I'm going quite slowly at the start and at the end. And then in the middle section, my gradient's a little bit steeper. So if I used the equation we've seen before, that would give me my average velocity. So I had a small velocity, a higher velocity, a smaller velocity. On average, it's still 16 kilometers an hour. But what if I wanted the velocity at each of these little sections I've drawn? And of course, we could draw a tangent. That's what my blue lines are, essentially. They're tangents. And I could extend that tangent and then try and work out the gradient of that tangent like this. But that would all be estimation, right? It would be relying on my sketching. And what we found out in calculus is that we don't really need to do that. We have something that does that for us. And that's where the derivative in calculus comes into this topic. Because now, instead of saying velocity is distance over time, what we can say is the velocity is the gradient at any point. And the gradient at any point is a derivative. And so we want the derivative. And in this case, and throughout this chapter, we're generally going to use the letter S for position. We do occasionally use X, but S is the most common one. And so we're going to use S for position or displacement or distance, depending on the problem. So I could also write this S dashed of t. So that's going to be our new velocity equation. We're going to say it's the derivative of the position, not just distance over time. And I can make the same kind of argument for acceleration. Acceleration is a change in velocity over time, so that's also a gradient. And so acceleration would be the derivative of velocity, or the second derivative of position. So we can either say it's the derivative of the velocity or the second derivative of the position, depending on what you're calling it. So we have two new, if you like, equations. Now this second one is in your formula booklet. Unfortunately, the first one isn't. So you have to remember one of them, but they give you the other one. And so let's use those to have a look at an actual example. Actually, before we do that, just one more thing. In the real world, problems would be three-dimensional. Yeah, and these equations would apply in each dimension. So, for example, if you were looking at a ship travelling on the sea, you'd be looking only at the X and Y direction because it's not really going up into space and back down again. Okay, but if you were launching a rocket into the air, you'd have all three dimensions. If you were throwing a cricket ball, you might have just X and Z. Yeah, because you would be throwing the ball kind of in a straight line. Okay, but all the problems we're going to look at are going to be one-dimensional. So we're only going to look at one set of equations at a time. So, for example, if someone's throwing a ball, we will be looking at scenarios where they throw the ball up in the air and it comes back down to the ground, and we're only looking at the height of that ball. We're not going to be looking at scenarios where someone throws a ball and it goes like this. Okay, that's not in the SL course. So let's look at an example. And I'm taking an example from the book. It's example 28 on page 266. But I haven't got it written out here. I've just got the little equation, if you like. And the first thing is, so it gives me the position of a particle in terms of time. It tells me that time can only be greater than 0, which makes sense for all of our problems here. We can't have negative time. It doesn't really fit. And then the first thing it asks me is find the position, velocity and acceleration of the particle after 1 second. So we want, didn't want my tablet to do that. So we want position at time 1. And that part's simple. We're just going to put 1 into this equation and we get 4. Meters is the units of our particle it told us in the question. When we want the velocity at 1, though, before we can find the velocity at time 1, we first need its equation. So we're going to use our little formulas that are in the red box to the left. Velocity is the derivative of position, so I'm going to differentiate what we see there. So 10t minus 4t cubed. And if I want the velocity at time 1, it's going to be 10 minus 4, which is 6 meters per second. And then finally it wanted the acceleration. And for that, we're going to use the second formula, that it's the derivative of velocity. So I'm going to differentiate that equation. So we're going to get 10 minus 12 t squared. And if I want the acceleration at time 1, it would be 10 minus 12, or minus 2 meters per second squared. And if we think about what this particle is doing, okay, so if I was to draw my horizontal line and put the origin here, okay, my particle, let's say, is currently here. And it is 4 meters away from where it started. It's travelling in the same direction, so if this way is positive, if I take to the right as positive, which we normally do because that's the way the x-axis goes, it's travelling 6 meters per second in that direction. Yeah, so it's travelling the same direction it's already moved. But its acceleration is going the other way. So it's travelling to the right at 6 meters, but because our acceleration is negative, it means it's slowing down. And if our acceleration and our velocity have different directions, different signs, then our particle is going to be slowing down. It means the velocity is going to go 1 second later to 4 meters per second, and then to 2, and eventually to 0 if it were to stay at this acceleration. And actually the acceleration is itself changing, so it's not going to be quite as simple as that. But we're just asked in part B to decide if the particle is speeding up or slowing down. We've done that. The next part of the question wants to know the values of time, of t, when the particle is at rest. Well, if a particle's at rest, that means it's not moving, and that means the velocity is 0. Yeah, if we come back right to the beginning to our cycling scenario, okay, we were at rest in this section here, where the position stayed the same, and since the velocity is the gradient of position, the velocity was 0. So my velocity expression that I used in part A was 10t minus 4t cubed. And that's going to be 0. And I want to solve that equation. Now, if this is on a calculator paper, you would either plug that into the equation part of your GDC, or you would graph it and find the 0. But we can do this ourselves. It's not too nasty of an equation. We can factorise it, so we can take out 2 and t at the beginning, leaving us 5, and then minus 2 t squared is 0. And if we solve that, we get 2 times. The first one is the time being 0, which doesn't really, it's true, it's one of our answers, but it's not a very interesting answer. Yeah, it started at rest. That's not particularly exciting, quite common. But this one here, we can also solve that. So 5 minus 2t squared is 0. 5 would be 2t squared. T squared would be 5 over 2. And so t is the square root of 5 over 2. And notice that I haven't put a plus minus here. And that's because we said right at the beginning the time was greater than 0. So we can't have negative time. So that's the 2 times when the particle is at rest. I'm going to skip part D because I want to spend time on part E instead. And part E is interested in the total distance the particle travels in the first 3 seconds. So if we think of what is happening to this particle, at the beginning, so S of 0 right at the start, if we want to know how far something's travelled, we certainly need to know where it started and where it is now. And at the beginning, so up here was our S equation. If I put 0 into there, I'm just going to get 0. So in the beginning, we've got 0 meters. We also know, and I'm just going to write it down here, that at time 1, we were at 4 meters. And it would seem to make sense to work out where we are at time 3, since we want the first 3 seconds. So our equation was 5t squared minus t4. So that would be 5 times 3 squared minus 3 to the power 4. And if you put that into your calculator, and you would be expected to use your calculator here, you would find out that you get minus 36 meters. So you might be tempted to say the distance travelled would be 36 meters backwards, because at time 0 we were here, and at time 3 we were here, so we've gone 36 meters. The problem with that is, well, let's just think actually of a little graph of this. So here's time 0 and the origin. So our particle starts here. The first thing our particle does, and we already know this because we looked at time 1, at the beginning, our particle travelled this way, and when t is 1, we knew we were at 4 meters. So already I can say I've travelled further than 36, because I know I've ended up all the way down here at minus 36 meters when t is 3. And I went at least 4 meters forward, so I've gone at least 40 overall, the 4 and the 36. And what I really need to think about, actually, is, well, I need to know how far the particle went before it turns around. And then I'll know how far I've gone overall. And that might seem like a lot of work, but we actually already know when it turns around. That is what we did in this question. Because if it reaches a velocity of 0, that means that it must hop. So initially, when we saw at time 1, it was going at 6, but it was slowing down. This time is when it reached 0, and then it must have gone back the other way, so the velocity would have become negative. So we want to know how far we went at that turning around point. And the turning around point will be when you reach a 0 velocity. So we can do S of root 5 over 2, which we would do in a calculator. Okay, so if you put that into the function in your calculator, so you do 5 times root 5 over 2 squared minus minus root 5 over 2 to the power 4, then you find that you get a number I'm looking for in the book, 6.25 meters. So the furthest point in the positive direction that the particle reaches is 6.25 meters. And so the total distance would be the 6.25 meters forwards, and then the 36, and then another 6.25 meters to get back to the origin. Yeah, so we have to go this way 6.25, back to the origin 6.25, and then finally the 36 backwards. And if you add all of that up together, you get 48.5 meters. So we can ask some quite tricky questions about kinematics, where you have to think quite a lot about, well, where is the particle? What way is it going? What's happening? I would certainly recommend drawing some diagrams, because that can help you sort of picture what's really happening to it. Even if it's only one dimensional, it still helps us see the problem. And although if you were to do the questions in chapter 13 here, there are no new concepts. They just mean that perhaps your function has a sine x in it, for example, or sine t in it, for example. It doesn't change the ideas, which is why I went back to the ones in exercise 5 where we introduced them for the first time. So I hope that kind of explains the concept a little bit more than someone just saying,